And I am the president. I hope. Oh, you see me? Okay. Well, anyway, let's all stand and do the Pledge of Allegiance first. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. Play ball. I'd like to welcome everybody here, especially those in person and on Zoom. We have a special presentation here from Manfred. We have a satellite. He's got a satellite receiver transmitter here, so hand it over to Manfred.
Thank you. Thank you, Carl. Okay, so all right. Well, let me first do a shout out to several amateurs who are invited. Actually, they may be online or maybe not. But W6PGS, Bryce Roberts, he's in the Bay Area. One of my colleagues and friends. He was the one who can take full credit for getting me back into ham radio after retirement. So a big shout out to Bryce. Second is Alan, AG7XS, one of my neighbors and friends here in Seattle. And the third is Kilo Golf Zero Delta, Dave Fisher, who lives in Squim. And you may remember him. He bought his pickup truck with a satellite station to Field Day last year to give us some bonus points. So I've been working with him rather closely. So welcome. Thank you for joining. Okay, so first, yeah, you might wonder what all of this is here. Okay, maybe it should just say hello to you all. See what happens here. So it's a satellite motion controller with currently installed two UHF antennas for 70 centimeters, two for simplex up and down links for the Green Cube satellite. And you can see it moves. And the other part of it is the ICOM 9700, which is in that box here on the table. And so I'll tell you all about this now in the next 45 minutes or so. Okay, there's no transmission, right? So no worries here. It's just saying hello. All right. Okay, so I see I'm already sharing my screen. You can share? Is my screen shared? Probably, huh? No? Okay, so let me do this now here. Okay. Maybe I should move this to the side. There's all this stuff here too. Okay. Can you see? Okay, I see. I'll move this out of the way. I'm not sure how to do that. Make it small. Yeah, okay. Unobtrusive. Takes a little practice. Okay, so all right. So what I want to present to you is about my portable satellite operation setup and portable operations in general. Because now, okay, I see here. No, it doesn't. I see. Oh, I have to click. All right. So a little outline, little introduction. Then I'll tell you about some software tools I've been using, the rotator design, how all of it got integrated into a system, and then what I did with portable operations so far, and some satellite roving I just did last week. Okay. Bless you, Steve. Okay. So I did work in ham radio satellite activities quite some while back. That was in 1981. I still already had some gray hair there, you can see. But that was the, yes, I know, long time ago. So that was at the DK0 UN, a club station we had at the physics department at the University of Cologne in Germany. And you can see there's an ICOM IC211E, the European version. And the antenna controller was this box down here. That is an 8080 microprocessor that we built in-house. It ran assembly code. So today we can, what is in that box, do in an Arduino, right? And the other computer up here with the big terminal next to it, that ran the satellite tracking software to determine where the satellites were, like AO7 or AO8. And it ran in some code written in spherical geometry. You know, there was no two-line elements back then. So that's how that worked. And then I took a break for a while and got busy with other things. And after moving over here in 1986, eventually I got back into it when the space station Mir and the space shuttles had packet radio capabilities. So I put together this portable station here and took that to Florida in this case to communicate with one of the space shuttles. It had in this briefcase I took on the airplane an ICOM 02AT, a little power amplifier, 30 watts, with a built-in LNA and a TNC, MFJ 1274, that is still in my car today under this driver's seat, actually. So I'm still using it today, some almost 30 years later. Right, so that was that. Then talking about some portable satellite operations, I didn't include any pictures here because I didn't have time to ask anybody for permission. But you can certainly, you all have seen pictures of people holding aero antennas in their hands and whatnot. And there's a nice article by Keith Baker, KB1SF, in the IMSAT journal, and you can click on this link here to see it. And then Archibald Delfisher, he's known as Del. You need to check out his QZ page, N7NW. He has done an amazing job carrying his 9700 in front of his chest and, you know, doing amazing numbers of QSOs that way through satellites. So that is really worth looking at. Okay, so all right. So first thing we need to know before we go portable is where are the satellites? You know, so it doesn't do you much good if you go outside and you don't even know what is where and when. So there needs to be an orbit model, which is a complex set of equations in that case. And then you need to get some matching input data into that model that tells you exactly what satellite is where and when it shows up over your horizon and so forth. And the orbit model is called the Simplified General Perturbations version 4, SGP4. And that was published by the Air Force in 1980. Well, it was this report, the so-called Space Track Report number 3 was assembled by the Air Force in 1980, and then it was published in 1988 by Dr. Kelso at the Air Force Institute of Technology, I believe. And that is for complete public release with unlimited distribution. And you can find, maybe I don't know how to get rid of this little thing here. Does anybody know? I don't want to destroy anything. We can. Oh, you can. Oh, that's good. Oh, okay. Okay, well, that's fine then. All right. Oh, that's right. So you can click on that link and download this entire report. And it contains a Fortran source code for this model that takes in these orbital elements in two-line format. And then it tells you where a spacecraft is. If you give it some time, And so the two-line elements look like this. It's 2 lines of data organized in a very strict format that is reminiscent of punch cards, which I'm sure which is where it came from. And you can see numbers here like this here, the so-called inclination that is 51.6 degrees for the ISS. And in this little animation here, you can see the orbit of the ISS around Earth, except that the Earth is turned off. So you can see what is going on. And so all of those elements here describe the size and shape of the orbit of each satellite, in this case, the ISS, and how it is oriented in space, right? So for instance, the last here, revs per day, that is the number that tells how many revolutions the ISS makes per day in its orbit around Earth. Right, so what that model does is it converts these elements angles mostly, and the time tag, which is very important where it is at that moment here, and gives out something called a state vector. A state vector is a geometrical entity that describes the position and the velocity of the satellite in X, Y, Z, three axes, X, Y, Z, where X points like along this green line here towards where the sun crosses the equator and at the spring equinox, and then the other two triads are aligned correspondingly. And then once you know what the position is and the velocity, you can do everything else you want to know. And you put in a different time, like a delta time from this epoch, and it then tells you exactly where your satellite is. So this was published in 1988. And when I became aware of this, that this was publicly available, I thought by myself, gee, this is too good an opportunity to pass up and play with. So what I did is translate that Fortran code into C, which was quite an effort actually, because it was quite messy, frankly. But I cleaned it up and wrote a C version of it, and not only the conversion from these angles to a state vector, but everything, including the rotation of the Earth underneath. You can put in your location, and it tells you exactly where the satellite is at any of those satellites at any point. And it was very, very popular for quite a while. It was for Linux, the first tracking program available for Linux. I did publish it, and there's still the tar file on the AMSAT FTP site. So if you click on this, you'll see it there. It has been sitting there since 1997. And it has been used by many amateurs around the world. Back then by NASA, various centers, and also by the European Space Agency. So Ken Harker wrote this nice article about it in the Linux journal back then. And I didn't know about that, but it was nice to see that acknowledgement. So it was not as fancy by any stretch of the imagination as today's software is. It had a basic text display like this, and a rather simple world map. And here you can see the Mir space station and the shuttle on proceeding towards the docking situation. So that's what I was playing with in the early 90s. Right. Okay, so with that, now what do we do today? Another big leap forward to build a satellite station, a portable one. Especially, you need equipment. You need software and antennas, basically. Radio, you need a radio of, oops, not too good here with the mouse controls. Sorry about that. The radio can be a simplex or full duplex radio, ideally with FM, SSB, and data capability. And of course, the ICOM 9700 is the equipment of choice, not cheap, but it does everything you need. And then you need some antennas, ideally with some gain and circular polarized. And you need software, right? So for Windows, there's PC32. For Mac OS, there's Mac Doppler. For Linux, you can get a gpredict or other modern versions, all integrated, fully supported. And then there are these devices like this SAT, a satellite rotator and rig control that is everything in one box. Very, very user-friendly, and a lot of people have this today. Right. So and there are apps for mobile devices too, like the one shown here to the right. Oops. Okay. Right. So why do you build a portable station? Motivation here. I've been playing with egg beaters for a while. I built these two shown up in the upper right in 2018 for mobile satellite operations, stuck with a magnet on the roof of the car. One is for the larger one, of course, for VHF, and the small one for UHF. And my wife said when she saw the small one, gee, that looks so neat, so cute, she wanted one too. And then eventually, you have to go out and set it up, and then you do a pass with the ISS, and that's all fine and dandy. but at some point you run into the limitations. So then eventually I put those into the attic. You can see here tilted at an angle of 45 degrees looking from Seattle. I think that is east. Where is east? I don't know. Yeah, that is east right here. You know, sort of at an angle to cover basically the whole US in some sense. And that worked pretty well too. But then I thought, okay, well, you know, it would be really nice to go out in the field and do it properly and get some real gain going and not beam through the roof or the walls where you get noise and signal attenuation and whatnot. So I had to come up with a solution, and I didn't find any a commercial solution that I liked. So I built my own, and it's always kind of fun to think about a project and build your own. So it should be lightweight and run on 12 volts, you know, for mobile or portable operation. And it should be strong enough to carry some decent antennas like these in decent weather conditions. So that is not made for putting up on the roof, you know, in wind or rain, but it's more like for, say, field day operation and things like that. Okay, so the rotator design, what you see here, it started with a breadboard from Ross that I bought. It didn't come from our kitchen. It was purposely purchased for $5.99 or something to play and then see what can be done. And then, as you can see, it's still there. Actually, it's a nice handle. Turned into an operational version in the end. I wasn't eager enough to redo it all since it worked so well. But in any case, so it has stepper motors, regular NEMA 17 stepper motors on the back side. Right now, you'll see the RF side, not the motor side in the back. It uses rhomboid flanged bearings. It uses gearboxes, planetary gearboxes, and then these little cog wheels and timing belts, pulleys and timing belts. So that was my thinking. I bought these items, and then I thought, man, is this really going to work? What about torques and how fast? You know, how fast should it go to follow a satellite across the sky? And how would I control those? And it did require quite a bit of research, actually. I'd never worked with steppers before, and I also never worked with Arduinos before. So that's why it took quite some time. But it was a lot of fun to do all that research. So here are some design calculations. So the steppers usually run at 200 steps per revolution. That is pretty common for all of those. And the maximum speed, it can be as high as 60 RPM, which is quite fast. But that was actually too fast for what I needed. So I figured, okay, well, I want a rate of 4 degrees per second. That's fast enough to track a satellite across the sky, maybe except at the zenith, and we can talk about that later, what to do there. So I made this spreadsheet to see, okay, given that I wanted to use these gearboxes with a factor of 10:1 and the pulleys with a factor of 3:1, see what that gives me here. And so if you then say it should cover 4 degrees per second in the sky, that meant you would have to run it up to a step rate of 533 steps per second, right? And that includes also a micro-stepping factor of 8. So micro-stepping, right, so if you run a stepper motor in single steps, like it's shown at the top here, it becomes a bit jerky, actually. If you run largish loads, mechanical loads like those types of antennas, it starts to vibrate, and then you get rather unpleasant effects. So on the other side, the micro-stepping, what it does is actually shown here. It breaks, the stepper motors are driven in steps in between the full steps, and you can choose various step factors, 1/2, 1/4, 1/8, or 32nd. And when you do that, it becomes very smooth, but you also lose your torque, right? So the torque is going down the tube. So you have to find some kind of compromise as to how much torque do you need, when does it start slipping pulses. is it strong enough? And so I came up with a solution that uses 1/8 microstepping, and that seems to be working fine. Another consideration is you can't drive these motors arbitrarily fast because they do have an inductance and they have a resistance, right? So that means they have a time constant. And down here you can see the time constant for that resistance of 1.5 ohm and 2.8 millihenry on the coils. You come up with a coil time constant of 1.867 milliseconds. So if you see up here, the pulse period, you can't hope to have a faster pulse period than what this time constant is, right? So then you steps. So I designed such that I'm just a hair above this or below this maximum speed rate that is limited by this RL combination here. So that's what went into the design. And then, okay, so how to control it then? I had no idea what to do about Arduino. So if you go online and you see the enormous variety, that gets scary, actually. I had no idea what I was doing. So I thought, okay, I'll start easy. I'll just take the smallest one there was and see where that gets me. Maybe it's enough, but I wasn't sure. And so I bought this Arduino Nano Every, and here you can see what it looks like. This came in a little package, and I put on those pins and put it on a little breadboard and started playing with it. And it does have an ATmega 4809 processor, quite a bit of memory for both code storage and data to work with. It has either 16 or 20 megahertz clock and plenty of I/O lines. So I started to develop some Arduino code, and I was surprised to find out how easy that is actually. The tools to develop Arduino software. Paul, gave us the presentation last. He's the expert here, I guess, on this. He knows a lot more about this than I do, but I just got started, and I found it enormously rewarding and easy to build code and load it into the processor and run it, right? So here's my test setup, little scope with trying pulses. The other thing is with these steppers, you can't just go to full speed and say, okay, I want them to move 1 degree over the antenna. Then you lose steps right away because there's mechanical inertia involved. So you have to work on ramping up the speed to full speed and then ramp it down again. So you wind up at 0 speed, nice and smooth at the target angle where you want it to end up. Okay, so right, so that is what was involved here. And now how you do it. So these trying to manage the pulse numbers is a bit tricky. Say for full revolution in azimuth, it needs, with that kind of arrangement, these gearboxes and the pulley ratios and the microstepping, it takes 48,000 counts for full revolution in azimuth for 360 degrees. And half of that in elevation for 0 to 180, 24,000 counts. So it's not a feedback loop that I implemented. It's just taking extreme care of how many pulses did it do in what directions. So we know where it should be, right? And that seems to be working, but it's a bit tricky to do. And it's especially tricky if you try to interleave motions for 2 different axes, an azimuth and elevation. So ideally you want to be able to move both at the same time, interleaved. And that is a bit tricky if you try to manage that by weight loops and then the steps fall on top of each other, so it becomes jerky. And so I found some code online that somebody did for CNC machines. And it uses interrupt controls, right? So the way that works is you set a certain timer, and then it expires at some point. It initiates an interrupt, and you run into your interrupt service routine, and then you can do what is needed there. So here's how how this scheme works, assuming if you look at the top here, these should be azimuth motor pulses. They can be very sharp. They should be very sharp, like little needles almost. And you can see here the time between these, this is a time axis, it gets shorter and shorter. That would be a case where it kind of ramps up the speed and then goes into a constant speed mode here for a while. And elevation may not be the same rate. It may go at a much slower rate in that case here. So what it does then, the software does is it figures out, okay, which pulse is the next one I need to execute. And then it does execute it, and it records the time when it did that, and then it figures out, okay, what is my next pulse? And in this case, it would be actually an azimuth pulse. So it knows, aha, the next one needs to be done here. So it sets the counter, it sets a counter to this point here, and then the processor runs at its full speed processor cycles, and when it hits the limit up here, 65,535, it creates an interrupt, and then in that interrupt function, a service routine, you can say, okay, now it's time to do this azimuth pulse. You record the time again, and then you figure out again, okay, what is my next one? So maybe that is azimuth again, right, in this case. So then it's a bit longer, so the counter has to be set to a lower value, and then it runs up and does it again, right? So that is how this scheme works, and that seems to be, I didn't come up with this, but I found it brilliant, actually, and I was really impressed. So it took a while to learn how the interrupt logic on this ATmega 4809 works, and I was able to implement that, and that seems to be working. And I'll show you in a moment too. We get some water here in a moment. The final electronic design is pretty simple. Everything is so nicely modularized, and these modules are so cheap to buy. So here's the processor, the Arduino processor. Up here is a Hall effect sensor. I'll talk about that in a moment. And then and there are two motor controllers made by Texas Instruments with the Texas Instruments chip. And they do pretty much everything for you. You just need to give it a pin with the direction that the motor should be moving and a pulse. And then it just makes sure the stepper motor that is attached here to these four lines, these two different coils, is just moving one step. Oh, it couldn't be easier than that. And you do that in elevation and in azimuth, two axes. And it has 3 pins here, M0, 1, and 2, where you can set the microstepping ratio. So I set it to 8, or 1/8, as I said before, which is accomplished by putting M0 and M1 to 5 volts and M2 to ground. And that's it. That's all you need, basically. And it needs a 12-volt motor voltage that goes in here and ground with a nice capacitor here across that is recommended. Then I have a little power supply that takes 12 volts in and puts 5 volts out for the logic. And then there are lots of LEDs. And I put those on because, these Arduinos, you can't just attach a terminal to see how they are moving and debug code. So, but it's nice to have LEDs that show you if it's doing what you think it should be doing. And then this Hall effect sensor is here to zero the elevation axis. There's a little magnet on the horizontal shaft. And when that gets close to this Hall effect sensor, it creates a voltage here that is read by the Arduino through that pin A2. And then it can figure out where in azimuth it should be going. In elevation, it should be going to 0. And it sees the motor, the voltage here from the 5 volts to see when the power is turned on. So that's how that works. There are LEDs, yellow ones to show the sense of direction for each motor, and blue ones to show each motor pulse, and some green ones to show if it's in motion, and another set of green ones here to show if it is within 1 degree of where you think it should be. So right, so that is the this part. Now what is in this box here? A lot of equipment integrated here. All of what you see here, except for the 2 laptop computers, is in that box. There's a ICOM 9700 here, and it has there's a little GPS receiver here that provides a frequency reference for this radio. And then there is a signal-link audio interface also that needs to be used for special applications. Because if you have software that is needed, say for packet radio that is only available for Windows, I can run that on my laptop, right? But I also can't talk with two computers to the same USB interface on the radio. So that is where the second one comes in here to do that. So in this configuration, there's the MacBook that controls the radio and the antenna, and the Windows laptop is doing the digital communications. It does have a PowerWorks power supply in it too, so that allows me to use AC like here, just plug it in and use it in a setting where there's AC power. And it has another GPS receiver here that is used, that's this one here. So you can see it's flashing green. It even locks up on the GPS satellites in here. And that provides time and location to this MacBook Air. And Mike will find it exciting to also see this CW capabilities built in, a Morty V4 CW keyer for Morse code to satellites. I should also mention the cables. The cable harness going to the antenna system here. There are 4 cables in it. There's the 2 RF cables for UHF and VHF. And then there's 12-volt DC power. And the third one is a USB cable to talk to the Arduino processor. And to make sure that it's not too long, this cable actually has a repeater at the end. It's an extension cord with a repeater at the end. So you can have a 10-meter long cable, and that works fine for any kind of application like taking it out in the field. Right, so here's what it looked like while I was having a good time scheming this all out, a little workbench. And here you can see the finalized product inside. The ICOM radio, the power supply. It came, there's a Novaxcom rack mount kit with a loudspeaker. Here's the GPS receiver for the frequency reference and the signal link. And back here is the USB hub, so you have only one cable going to the laptop that talks to everything inside that box. And then here's what it looks like from the front. Right, so then antennas. Those antennas, those 2 WIMO X quads, that's what they're called. So for Green Cube, I like to use both of them because it is a simplex UHF uplink and downlink. So you get 3 dB gain out of this setup. And to combine the 2 polarizations from both antennas, there are 4 ports. So I found this this 4-way splitter from RFM design, which transforms, those all 4 ports together onto a single 50 ohm port. All of these N connectors are 50 ohms, and it uses quarter wave transmission lines to make sure you can have 50 ohm on each port. So here you have 2 50 ohms in parallel. That makes 25, and here you want to have 50 ohm coming out, so you need to have 100 ohms twice in parallel. So that piece of transmission line is a 50 ohm transmission line because the geometrical average of 125 is 50. So very convenient, very clean. Yes, and these antennas have quite a bit of gain, actually. They're pretty compact. I also have the 2-meter version, which is a bit bulky to carry around, but it looks great too. All right, so then what about preamplifiers? You need to be careful with satellite communications that you don't spoil your signal by having a lossy cable in front of your receiver. Because it really buries the satellite signal in the noise unnecessarily, and there's no way to recover that once it is lost. So you need to have a low noise amplifier as close to the antenna as possible to make sure you boost up the signal, and then after that you can stand some amount of loss pretty easily. So these cables here are RG8X. That's what I use. That's not ideal, but they are easy, flexible, and carry around, so forth. So that all works fine. These amplifiers, there's one for VHF and one for UHF. You can see them there. They both have 24 dB gain, a pretty low noise figure, and an RF box built in that works up to 100 watt transmit power. has protection, and it can be supplied. The DC voltage is supplied directly through the coax cable. And fortunately, the ICOM radio has that capability built in. You just turn it on, and it feeds the preamps with DC voltage. Very clean. So then then I also have some filters there. Those Comet filters. That helps to not have much of desensitization, where the transmitting antenna bleeds into the receive channel and causes noise. So that's why those are there. All right, so here is what it looks like assembled in the field. The front side, you can see. The back side, the other side has the motor electronics and or the mechanics for the motion. And that was some pictures from Fort Flagler during field day. So let me see, I wanted to show you something else. Let me get out of this presentation here for the moment and do something else. Okay, so let's see, we'll move this antenna first back to 0. So you can see there's a pretty simple command language. You just say SL 0, 0, right? That means 0 degrees elevation and 0 degrees azimuth. Hit return. That goes, huh? Very quiet. Yeah, very smooth. Smooth is the word, actually. So that's what it's doing. And you can also say SL question mark just to give you an idea, and then it tells you where it is, right? So it is currently, it's still at, these counts are in milli-degrees. So 52.013 means 52.013 degrees azimuth, right? And so now it arrived, right? So if I say SL again with a question mark, 0, 0, right? That's what it should be. Okay, so now again, let me get out of this here. Now we do something else. Now I bring up this. So I showed you earlier the SAT-track interface that for this version that you can find the source code of on the AMSAT server. It looks like this. So now it is currently tracking the International Space Station, right? So let me see if this works. If I can connect to this. Yeah, sometimes it's tricky with these USB ports. When one application, the one I just showed you, where you can talk to it directly, releases the port, and then you try to connect. Let's see if that works here. Oh, okay, right. So now there's another artifact that you saw. What happens is the Arduino has a funky habit. When you connect to the USB port, it does a full reset on the hard boot, you know, and then when that happens, it resets everything. So the antenna under the weight of those cables is not perfectly balanced. It's going up, you know, and when the motor is turned off, there's not enough tension to hold it wherever it is, so it just went up. But what you can see now is it says, okay, well, that was fun, but let's see, I need to really be down at 0 elevation. So it went after a little wait period. It said, okay, I need to go down in elevation and find where that Hall sensor is. And the Hall sensor has some kind of bathtub type function. When you get with the magnet close to the sensor, it goes down in voltage, and then it's kind of flattish, and then it comes up. So it runs into it, and when it says, I'm in the bathtub now, then it says, okay, stop, and then go very slowly to see where it comes back out so you don't overshoot. And then when it sees it hits the threshold, it says, okay, here I am, and that's it. And then from that point on, we know where that Hall sensor is installed, and the magnet is screwed onto this shaft. From then, it needs to just go down, say, 17 degrees, and then it knows for sure, okay, that's where it is. So here you go. Ready to go. And so that display shows the space station to show up in 47 minutes. That's quite a while. I was kind of thinking it came earlier. Maybe I didn't do this right. But okay, well, let's see. We can get out of this. This is the single satellite display. You can also hit an M, and it goes back into the multi-satellite display. So maybe we'll select JO97 instead, right? You just go up here. Simple-minded, old style, 1980s or early 90s cursor controls in a text window. That's what that is. But it works, right? Right, so hitting a V, can't open it. Okay, this is already not good. Okay, well, it would show a polar display where the track is across the sky, but maybe I can figure that out after the talk. We can play with it some more while Scott has his VE session, or after the business meeting, actually. But meanwhile, let me go back to my presentation here and see where we need to be going here. So that was field day, right? Field day. Okay, so what about satellite roving then? This is really getting fun. Roving usually means you go out in the field and you go to some place to activate a park or a rare grid and operate from that location, and then have others collect these grids or whatever it is, points for their VUCC awards and things like that, right? So it's also fun to get into nature and away from urban noise and have a good time, and you may even be able to collect points for yourself. If you're in a rare grid, people will call you, and that may come from a rare grid you haven't worked yet, right? So you have to watch out for the award rules. For instance, for the VUCC, it only counts if you are within 100 kilometers of your home QTH. So you have to be careful to make sure that happens. For the worked all zones or DXCC, you can be anywhere in the US in your own DXCC zone. Right, so operational considerations, you have to make sure you're prepared. It gets very frustrating if you go out in the field and then things break down, or you forgot something, or you spend all your valuable time, scratching your head and getting upset in the end, so frustrated at minimum. So be prepared, make sure everything is working. Then you need to develop a schedule for satellite passes, so you know where to be at what time, what satellites will be in the sky. And then also you want to pay attention to your personal limits, not overdo it. Break for meals, that gets forgotten easily in the heat of activities. You need some rest time. You need to take into account your own personal conditions and whatnot, and safety, right? Very important. Don't operate while driving. That is really dangerous, right? And don't do any stupid things, right? Use common sense and watch the weather. You don't want to get caught, in a situation where it gets unpleasant, or if not dangerous, right? And then there's trip planning, like figure out a route, points of interest, distances to drive, road conditions, and what do you do overnight if it's an overnight stay? And make sure your car is working too. Don't forget that. Check your oil and tires and who knows what. And take along some supplies like personal items, test equipment, small tools to make repairs in case something does go wrong and you need water and food and all of these good things. So that is what roving looks like to me. And so here is a motivation to go roving. So this is the AMSAT Gridmaster Award map. The Gridmaster Award is the equivalent of what people do at 6 meters with the Fred Fish Award, where you get an award for having contacted all, I think it is 488 grids in the continental US, right? So the satellite equivalent of that is called the Gridmaster Award, which is very sought after, but it takes a lot of work and it takes a long time too. So this is shaded such that the areas in dark green are those that are probably highly populated, so people have had contacts pretty easily with those. But when it gets into the yellows or browns, those are sparsely populated areas where there's hardly any amateur unless somebody ventures there on a roving trip. So you can see in the Pacific Northwest here, we have quite a few of those, and especially down along the coast. There's one here, Charlie Mike 79, I think it is, that only has a very tiny piece of land in Santa Cruz, right? So that's a good one to go to, make people happy. But what I did is I figured, okay, well, what if we're here in Charlie November 987, so what if I go up and cover those 4? right? On a 4-day trip. So here's my as-driven route using the iPhone APRS app to record it all. Mukilteo, that's when I started on October 11. That is still in our home grid, so I wasn't too far away from home yet, and could check out everything, make sure I could still go back in case there was a problem, right? So I hung out there, got a nice IO117 pass with, towards the northwest, and did some DX there. And after that went all well, I went to Granite Falls, my second place, and there I stayed overnight, two nights actually, had a full day and a half. So that place is still within 100 kilometers from the home QTH. So it is fully VOCC accountable. And but it is in a rare grid, right? So you can see most of that grid is all the Cascades, and nobody's living there except for a few small towns. So I spent there a day and a half, and then I ventured here into an area where I've never been before to take a look at the North Cascades National Park, which counts as that location at the Ross Lake Overlook counts as a dual POTA activation for both the national park and also for the Ross Lake, the National Recreation Area. And then I went over here. It was a fantastic drive to the Loop Pass, ski snow park. And that is a new grid here, Delta November 08, one of those rare ones. Did some passes here. Then I stayed overnight in Okanogan. And then the next morning, got up really early to go to this grid line here in Dyer, in the middle of nowhere in Douglas County. That was kind of fun, actually. You'll see pictures in a moment. And then I went down to Quincy, that counts for both grids here, right? And then I went down to Quincy, which is in Grant County, and then back home. The last stop was at the Cle Elum rest stop on I-90 in CN97. All right, so Mukilteo, here's my mobile setup in operation with that box on the strapped in, with the safety belt on the passenger seat. And I had this laptop here for the satellite operation, and then the Windows laptop to run the software for IO117. It was raining, but it looked promising weather-wise, so everything worked. Time to move on. Then I spent those 1.5 days in Granite Falls. They found this empty lot that they apparently had just started to develop for a new subdivision. And so I had no hesitation to say, hey, this is on a hillside, perfect, right? So I just drove on the grass. There were already truck marks in the ground and bulldozers parked. So I thought, okay, this is cool. And that worked fine. Here's a picture in the other direction with a cloud coming above Mount Pilchuck. It's kind of interesting. Looked like something severe had happened there. And this was at the farm where I stayed for 2 nights. Very nice view. Some trees, but clear horizon. And here Mount Pilchuck in the early morning east. This was the second location, the third location, rather, the Ross Lake Overlook. POTA IDs are listed up there in Charlie November 98. So here a green cube just grazed the along the horizon here behind those trees, but it was enough for 13 DX QSOs, mostly with Japan actually, it turned out, and then it disappeared behind this ridge here. So it was just enough for valid POTA activations, which is 10 is the minimum QSO count. And then I went to the Loop Pass in the Okanogan Wenatchee National Forest. And it was really beautiful here seeing these large trees coming out in yellow, so I had a great time driving around, and all of these were rather popular on the radio in FM or SSB or in data. Had a great time on that trip. Here I'm at the Quality Inn in Okanogan. I didn't care, if the bed was comfortable. I just wanted to have an outlet nearby to recharge the power station in the car, and a safe parking lot where I could set up the antenna to have some more evening passes. So that's what I did here. you can see, nighttime or late evening operation. This is the Gold Zero station I use for the radio in the car, for the non-vehicle, power users, which is that box primarily doing this operation. And I brought a long extension cord. I asked the lady at the desk, can I plug that in somewhere? She said, sure, right next to the pool. Well, outside actually, so it's not near water, but I found this, plugged it in, and it charged all up overnight. So that was all very successful. And then came the big one. So Dave, KG0D, he gratefully advertised my roving plans on Twitter, or X now, and it went viral in Japan, actually, turns out. Hey, what am I getting myself into here? Oh boy. Okay, we'll see. So here you can see on this country road in the middle of nowhere, that was the morning of the partial eclipse actually also, which you couldn't see much of because of the clouds. But in any case, the Theodolite iPhone app is very helpful to get your bearings. It shows you exactly where you are. And so for the VOCC rule is if you activate 2 grids or even 4, some part of your operation needs to be in each of those grids that you activate, right? So in this case, the car and the operator and the radio and everything is in DN07, and then the antenna, this contraption here, in DN08, and the grid line is right in between, right? So looking west. And then came the pass, IO117 came over the horizon, and I dared to call CQ. And here you can see that is the GUI, so I used the call AG7NR/R for roving. And you can see all these calls here from Japan coming in. And then Dave, who acted as my wingman, essentially from home, he texted me some minutes into this show, and he asked, is there a problem? Because he hadn't heard from me, right? I just couldn't get a word in. I may have to tweak the timing, the Vox controls for turning the transmitter on and off. That's probably too long. So that may be part of it, but I just couldn't get a word in until the pileup subsided a little bit. And well, if you know how pileups work in SSB or CW, you hear maybe half a dozen different stations or more, but you can catch fractional call signs and then call back, say, W7 ? And then hopefully you get a single response. Well, in the digital realm, that doesn't work. You're right, it's a simple, the channel gets clogged up immediately in that case, and you can't get a response in, and then you're screwed, right? But eventually I did get responses in, and you can see here that there were some at the bottom. Eventually it cleared out. And these green queue passes are pretty long. They can be easily an hour long. So there's plenty of time. No need to panic, actually. And this software also has a nice feature. It has this traffic window, QSO viewer, which shows you who all is having during this pass, say, a contact with whom, and what state of the contact is it in. Did somebody call another station? Was there already a valid two-way exchange? Is it all done? In which case it would show green, right? But if it's black, all of those, and I'm down here, actually. You cannot really see it well, but that is my call here. So you can see the whole world is trying to get hold of me, which was quite... Oh boy, okay, so that was exciting. Then I moved on. After that pass was over, I moved down to Grant County, across the county line, and it's in the hills northeast of Quincy. You can see it's a beautiful country. It's just farm roads and non-paved farm roads, but a very clear view of the horizon in all directions from up there. You can see down here, that is Moses Lake, right? Glistening a little bit in the sun. So there's I-90 going across here in the middle of Moses Lake through there. And Quincy is over there. So that's where I spent another few hours and a whole bunch of passes. And then I went to the last stop for the day. I spent 7 hours at that rest stop, the Indian John Hills rest stop on I-90 outside of Cle Elum. and there were some people coming, right? So we didn't have free coffee, but like what Robert did with the other restaurant, we'll talk about later. But it was fun. Captured, and then I was back home at 1:30 in the morning or so. So total QSO count, unbelievable. More than 400 satellite QSOs in 4 days. So for more than 100 on average a day. So that was quite fascinating, actually, and completely unexpected, but it was pretty cool. So I really enjoyed getting out into the mountains one more time, before it gets cold and unpleasant. And that was sort of my makeup trip for missing the salmon run this year. All right. Okay. So yeah. So are there any questions? Well, while I was driving, the sun came out just briefly, and I just glanced at it while I was driving, and it was partially eclipsed, yes. But I looked only once, and I thought, okay, I'll save my excitement for April 8 next year, actually, with the full, solar eclipse in Texas.
I didn't see any phones set up around. Aren't you concerned about people getting there?
You're right. Right. So at the rest stop, it was pretty on the end of it. There was nobody there, far away from people. And in that hotel parking lot in Okanogan, I did set up warning markers with these cat's eyes, red cat's eyes. Yes, they're just running in the picture yet.
Setting the
antenna.
Is there a benefit to having the surrounding area as flat as possible, or should you be looking for hilly areas where you go to the top of the hill?
Well, ideally, you want to be on top of the hill. So because when the satellite goes down near the horizon, you have the farthest contact opportunities. In case of Green Cube, since it's up more than 5,000 kilometers, if it goes down to the horizon and you can still reach it, you can talk or send messages back and forth, I should say, all the way from here to New Zealand, all the way from here to India, or to Azerbaijan. That is 12,000 kilometers away, right? So you want to be able to look down as far as you can. So if there are mountains, you get some coverage, but not that far, right? So that is your goal.
So looking back, if you think it again, would you distribute the azimuth and elevation across two different regions?
I thought about that, actually. I thought about that last night. Why didn't I do that, actually? Well, I do like challenges, even though I mean, if you want to get into operations right away, you're much better off buying a Yaesu rotator, which is heavy, but also expensive, and an SAT controller, and you're done practically, right? And you go out, you set it up for a few days. That I like technical challenges and building things and making it work, and so and then play with it, of course, too.
You mentioned you didn't have a feedback loop.
How
long can you run before you have to go back to origin and figure out zero again?
Okay, that's a good question. Actually, you can do that quite often. I mean, these antennas don't have they're not like a laser pointer. You don't need to be accurate within a fraction of a degree, but you can see visually if they are not making it back after a full day of running around. But I haven't seen that, actually. It is pretty reliable. I mean, they may be losing a few counts here and there, but that doesn't make a difference, really. Right, and I should also mention it has in terms of rotation, it can go full rotation in one direction and also complete full rotation in the other direction. So 720 degrees total, right? And the middle is 360 where it is pointing now. So that means you don't have to deal with a hard stop at north that many antenna rotators have. And then if a satellite path goes across there, you have to rewind, all the way. By the time you get there, it's gone, possibly, right? So that design, the software is reliable enough that it doesn't wrap the cables and destroy anything. And I checked that many times. It's pretty reliable.
Have you ever used this satellite?
No, I have not, but you certainly could.
Have you tried Earth movement with this?
Not yet. there are some stations and Dave from KGZOD. By the way, thanks for his remote support here. He has done that. He has built some fantastic Yagi antennas that can be rotated around the axis to match the polarization. And he has had successful contacts EME with one of those giant super stations in Germany. There's one that has, I think, 128 Yagi antennas on a huge frame. So if you have a super gun on the other side, you get away with that. I'm eager to try that, but I haven't done yet. Anything? For the next, I'm planning to write this up for the AMSAT journal too, so, but there will also be a briefer version for our own newsletter.
So I'm not sure people online can hear your questions without the microphone. So
Oh.
Either repeat the questions or we'll pass the microphone.
Okay.
Around.
Are there any questions from anybody online? Can't possibly be that I said everything and there are no questions. No?
Hey, Manfred, Whiskey 6 Papa Golf Sierra here online. I tuned in a little bit late, so you might have covered this, but since you were talking about operating at your first stop on your trip in the rain, did you talk anything about the waterproofing of the antenna that's outside the car?
Hi, Bryce. Nice to come online, and thank you for joining. Well, here you can see, so it's open. If you don't do anything, it's open at the top right now. I haven't built a roof yet, but I did bring along a full roll of saran wrap, right? So you can see that here. And when there was rain forecast at that stop, I had it all wrapped actually before the rain started. So you can see it's pretty wet there. Yeah, thank you, Bryce. Good question.
So Manfred, this is Whiskey 7 Romeo Oscar Victor Ross online. Could you tell us a little about how you compensated for the Doppler shift between your station and the satellites?
Yes, yeah. So the software, let me get out of it here. The software is doing all of this. There's Tevel. Tevel. Let's track a little bit of Tevel here. Tevel 7. Okay, turn on. Now you can see. Speaking of Doppler shift, the people online can't see it, but this laptop, the software talks not only to the antenna rotator, but also to the radio, and it calculates the so-called range rate, which is the rate at which the satellite is coming at you or recedes away from you, similar to when you hear a fire engine drive by and you can hear the pitch change, right? That can all be calculated if you know where the object is and at what speed it's going. And the software calculates that, so it also knows where you are, so it knows exactly what range rate you have between the satellite and yourself, and then you have to manipulate both the uplink and the segmentation fault. How about that, huh? Why is the segmentation fault? Okay, now I'm of course embarrassed here, but that hasn't happened before. Of course. What do you know? But so Ross, to answer your question, right? So one can calculate all this, and the software has taken care of that. I haven't tried this mode in years, actually. There's another. Okay, so we'll do this differently here. This is probably not, oh no, it's working. Okay, so here. All right, so this is the version that does use a GUI, right? And the two-line elements are a bit stale, but okay, so if I turn the tracking on here, this is the version of the software currently that has a GUI. You can see, so now it is, I see, okay, now it is doing this again, because now a new tool connected to the Arduino, and it did a reset again, so it needs to find its home again. And of course, it's doing that supposedly at as 0, so there's a little. Okay, so that is azimuth zero, no, it's going down, and once it has gone down, it will then presumably assume tracking AO7, which is about to disappear behind the horizon here. Oh no, it's coming up actually. You can. Yes, but it's not too probably. It's looking right at Steve. Yeah, it's looking through buildings. You know, that is not efficient here. We can check if this one is any better. Tablet 7. I'm not sure it is on. You know, so these tablet satellites are not all on at the same time. So I'm not sure. But in any case, it tries now to catch up with it, and then it follows it along this track down to the horizon. I hope I answered your question, Ross. Is there anything else? We're actually over time already, no?
Thanks, Manfred.
Okay. There were 8 minutes over time.
Good job, man.
Thank you. Okay,
And doesn't need you to close that.
yes, you're right. Stop share. Thank you everybody online who was listening, especially the guests from California and elsewhere. Okay.
Okay, we're gonna start the business side at 1:15. So take a break, fast break. And we were gonna pass out a test of all the theory that he talked about. But you're lucky because we got to go to the business meeting.